Alright, just as promised in the previous presentation on series expansions for analytic functions, we're now going to talk about some expansions that involve negative exponents. And of course, we're not doing that just for the sake of throwing around negative exponents. It's because we want to, as we're going to see here, we're going to expand in situations where, say, a function is analytic everywhere on and in a circle except for the center. And well, if that is the case, if a function is analytic everywhere on and in a circle except for the center, then we cannot apply the Cauchy-Goursat theorem or Cauchy's integral formula to integrals of the function around the circle, and that's because, well, we've got that place, that center, where the function is not analytic, so the hypotheses of these two results are not satisfied. But at the same time, if we look back at Cauchy's integral formula, the integrand in the formula was f of z divided by z minus z0, and that thing is not analytic at z0, which was inside the contour too. So, and of course the Cauchy integral formula, that was still a useful result. So apparently there are situations in which we can deal with a singularity at the center of a circle, for example. And in this presentation we're going to take a look at how an isolated singularity, and that is a place where the function is not analytic, but it is analytic near it, so it would be a situation where the function is analytic in and on a circle, except for the center. So how an isolated singularity can be handled, well, and then let's just say can be handled in terms of series expansions. And yeah, that's what it is. We will obtain a power series type expansion, but it will involve negative as well as positive integer exponents. And we're going right away to the theorem. The expansion is called the Laurent expansion, after another French mathematician. Well, it says the following. We take 0, smaller lowercase r, smaller capital R. We want z0 to be a complex number. And we want the function f to be analytic in a region that contains the annulus. And remember, an annulus is a ring. The annulus, so that r is smaller or equal than the absolute value of z minus z0 is smaller or equal than r. So this is the disk of radius capital R, out of which the open disk of radius lowercase r has been removed, and that's a ring, or with the corresponding Latin word, an annulus. Okay, we want c sub r to be the circle of radius capital R around z0. And c lowercase r to be the circle of radius lowercase r around z0, and we want both of them to be positively oriented. Then for any z in this annulus, and the annulus A is supposed to be this thing here, and we're back. So the annulus A, as we want to call it, is given by this equation that we've just talked about. And for any z in this annulus, we have the following. We have that f of z is 1 over 2 pi I integral over c sub r f of x divided by x minus z dx. And that would just be Cauchy's integral formula, so that can't be right. And so the complete formula is that we also have to subtract 1 over 2 pi I integral over c sub r f of x minus z dx, and that's the whole formula. And we're going to also show now on the rest of this panel a variety of other ways to express that. Before we go there, well, first we notice that this is very much like the Cauchy integral formula, except that we're now subtracting the integral over the smaller circle, and I think this is the first time that we're encountering this symbol here. Well, that one's not going to highlight nicely. This integral with a circle in it. That's just a regular integral. It's just that in older texts, as well as in applied texts, and specifically in physics texts, often an integral over a closed curve or an integral over a closed surface is denoted by that circle, which simply says that whatever you're integrating over is a closed entity. Now, as far as I recall, I'm not going to use that symbol too often, but I thought I'd throw it in at least once, so that if/when you see it somewhere else, you're not going to be thrown off. There's nothing different about that integral. It just indicates that we're integrating over a closed curve. Okay, now these terms can be translated into something else, we have seen in our presentation on series expansions that the term that looks like the Cauchy integral theorem can be turned into a power series, and it turns out that the other term, which goes over the circle that is too small, essentially, that one can be turned into something that looks like a power series only with negative exponents here. And because one starts at 0 and the other one starts at 1, we really just hit every integer exactly once in this summation, in these two summations. So this can also be written as the sum n equals negative infinity to infinity a n z minus z0 to the n, where n can now also be a negative integer. And for the coefficients, well, the coefficients have got to be similar, and in fact are the same as the coefficients that we had from the Cauchy integral theorem. A n is 1 over 2 pi I integral over c f of c divided by c minus z0 to the n plus 1 dc, and that's for all integers n. And if you want to puzzle it apart, well, then bn is of course a negative n, so you could put a negative number in here, which then actually is no longer a division but actually a multiplication by c minus c0 raised to some positive power. So bn is equal to a negative n for all positive integers n, and c is any circle around z0 whose radius is in the interval between r and r. And so that means what we'll do is we'll first prove that these coefficients can be computed with this thing being either c lowercase r or c capital R, and then we're going to show that those circles can be replaced with any other c also. Okay, well, let's start out and let's take a look at this. Let's find ourselves a z0, and for the sake of this picture, let this be CR, and notice that this one is actually positively oriented, so we're going negatively oriented, so actually we're going backwards around that thing. And then we have C capital R here, and that one's positively oriented in the picture. And we know that Z is somewhere in between. Now, if we want to apply something that we know, such as the Cauchy integral formula, we somehow have to avoid this point Z0. And we already have seen, as we have worked with Cauchy's integral formula and various extensions, how to do that, and that is you simply link up the outer contour with the inner contour and turn the whole thing into a contour with a uniform orientation. That is why on the outside we go positively oriented, then we go along this straight line segment, and then in order to continue in the same fashion we have to go through c lowercase r backwards, then we go out, and then we complete the circle around CR. Now this contour is one so that f is analytic on and inside that contour, and that means we can apply Cauchy's integral formula, and by Cauchy's integral formula that means that f of z is 1 over 2 pi I times the integral over the outside plus the integral over this segment plus the integral over that segment, and those two integrals, as we push this little gap closer and closer together, those two go away. And then we have plus the integral over CR with a negative orientation, and that would be minus the integral over CR, where we keep the positive orientation on CR. And that already proves the first formula in the Laurent expansion. Now what we need to do is we need to turn these things into these power series. For the first term, that's going to be pretty much exactly the same argument as what we had before. Let's go through that. If you have the first term, 1 over 2 pi I integral over c sub capital R f of c over c minus z dc, well, then we expand with z0. See, we've subtracted z0. It doesn't want to highlight, right, but you can see we've subtracted z0 here. And then we subtract negative z0, and that means we have only added 0, everything else is the same. And now we're factoring out a c minus z0, I think. Yes, we're factoring out a c minus z0 in the denominator. And now we realize that, you see, z minus z0 in absolute value is smaller than c minus z0 because z is closer to the center than the points on the outside circle, and that's what's going to make the argument work. But first of all, that means this thing has absolute value smaller than 1, which means we can expand this expression into a power series. And we do that by, of course, keeping the factor out front, keeping the integral, keeping this factor, and then realizing that this last term is the sum n equals 0 to capital N, z minus z0 over c minus z0 to the n plus the sum n equals capital N plus 1 to infinity z minus z0 over c minus z0 to the n. That breaks up into two integrals. On one hand, in the first integral here, I can take out the finite sum. I can take out the z minus z0 to the n, and I keep the 1 over 2 pi I integral cr f of c minus c0 to the n plus 1 dc, and that's of course the coefficient that we want to. Plus, well, then we have 1 over 2 pi I integral over cr f of c divided by c minus c0 from here. And we're factoring out a z minus z0 over c minus z0 to the n plus 1. And that means this is now a sum of powers that starts with 0 and goes to infinity, which means this is again 1 over 1 minus z minus c0 over c minus c0. And in order to show now that this term is this sum here with n replaced with infinity, we simply have to show that this last term here goes to 0 as capital N goes to infinity. And we can do that because z is fixed and z minus z0 is smaller than r, and r is equal to c minus z0 for all the c on cr. That means there is a q smaller than 1, so that z minus z0 over c minus z0 absolute value is smaller than q for all c on cr. And that means the absolute value of that last integral is less than or equal than what we get when we pull the absolute values inside. And then again here we're integrating against the arc length. That's what this symbol means, at least in anything I present. And now we just pull this part out, because now we know this guy is bounded by q, right? So we end up, as we put absolute values around every single factor, we realize the absolute value of z minus z0 over c minus z0 to the n plus 1 is smaller or equal than q to the n plus 1 times this integral. And this integral, we realize, is just a number because we're integrating a continuous function without singularities over a circle. So this is a number times q to the n plus 1, but q was smaller than 1, which means as n goes to infinity, this will go to 0. And that means we've got the first expression. We have that the first integral is equal to an infinite sum with to a power series with the right coefficients. Now we want to look at that second infinite sum, and we're going to keep the minus sign with us just to make sure everything stays clear. And we're going to do a similar expansion, namely this time we're going to pull the negative sign in and get z minus xi, right? And then we subtract z0 and subsequently subtract negative c0. So that means that these two expressions really are the same. And so the only difference between what we had done for the first integral and the second integral is that this time we've got the z here and the xi here, where previously that was the other way around. And that's because on c lowercase r, we have that xi minus c0 is smaller than z minus c0. So that means we're pulling out a z minus c0 in the denominator now. And we're ending up with very similar expressions, only that now we have 1 over 1 minus xi minus c0 over z minus c0. And again, we expand that into a power series because xi minus c0 is smaller than z minus z0 in absolute value, so we can do that with the geometric series. And again, we break the power series up. So from here to here, we keep the factor, we keep the integral, we keep the factor in front of this expression, and then the expression once more is the sum n equals 0 to capital N, xi minus c0 over z minus c0 raised to the n, plus the sum capital N plus 1 to infinity, xi minus c0 over z minus c0 to the n dxi. And again, we break those two up. On one hand, we get the summation n equals 1 to n plus 1, and here is where I have to be a little bit careful, because I did an index shift at the same time, and that's because I wanted to fit everything on one panel. So let's see, this is of course just the first sum, but what do we see in the denominator? Because of this z minus c0 here, we actually have a denominator of the form z minus c0 to the n plus 1. Okay, so that means the exponents start at 1 actually, 0 plus 1, and end at n plus 1, capital N plus 1. So that means our sum actually is from 1 to n plus 1 with the z minus c0 to the negative n, because the z minus c0 are in the denominator. And so basically that means in this replacement we have replaced n plus 1 with n, and so now the integral still has the 1 over 2 pi, still has the integral 1 over cr, we still have the f of c in the numerator, and we have c minus c0, and if we replace n plus 1 with n, then n is replaced with n minus 1, and so that would be c minus c0 to the n minus 1, and if I shove that into the denominator to have the same form as before, then the n minus 1 of course becomes negative n plus 1. Okay, that was a lot of hand waving, if you will, but it is something, if that didn't quite work out, it is something I would recommend you just do the substitution k equals n plus 1 on a piece of paper, work it out explicitly. This is the kind of thing that as you read, for example, you want to be able to do mentally, and let me be honest, every so often when I read that, I just have to take out a piece of paper too, or write it into the margin of the book just to make sure I know what's going on. Okay, so as before, that was the finite sum, and now we're dealing with the infinite sum here. And yeah, I didn't lose the infinite sum. Now I'm getting panicky here. Well, we've got the 1 over 2 pi I, we've got the integral, we've got the f of c over z minus c0. We pull out c minus c0 over z minus c0 to the n plus 1, just as before. And that means this sum here starts now at 0, goes to infinity, and that means it is just 1 over 1 minus c minus c0 over z minus c0 by the geometric series formula. And just as before, this is basically what we want. The coefficients are in the right form and all that. We now simply have to make sure that that last term goes to 0, and we're going to do that in exactly the same fashion as before. Because z is fixed and z minus c0 is greater than r, lowercase r, and lowercase r was c minus c0 absolute value for all the c on the smaller circle. We have that there is a q smaller than 1, so that the coefficient c minus c0 over z minus c0 in absolute value is smaller than q for all the c on zr. And that means that this big integral, we apply the triangular inequality, and again then the integral turns out to be an integral against absolute value c prime of t dt, and I don't want to go to a parametrization, so I use this notation here. And we have the absolute value inside now. We realize this is bounded by q to the n plus 1, and everything else just stays the same. And again, we realize this integral is just a number, and that number is independent of capital N, and we have a q smaller than 1 to the n plus 1, which means this whole thing, because q to the n plus 1 goes to 0 as capital N goes to infinity. And so that means that f of z is equal to the first integral over the outer circle minus the second integral over the inner circle, which were sum n equals 0 to infinity z minus c0 to the n at 1 over 2 pi I integral over c sub r f of c divided by c minus c0 to the n plus 1 dxc. And now we simply have the other one, sum n equals 1 to infinity z minus c0 to the negative n 1 over 2 pi I integral over c lowercase r f of c divided by c minus c0 to the negative n plus 1, and that turns out to be the sum a n z minus c0 to the n plus the sum over the b n z minus c0 to the negative n, and that then means, and the coefficient a n and b n are as claimed, because if I were to go with n equals negative 1 to infinity, then this would be a plus n here, and this one would be a plus n here too, and then the coefficients a n are as claimed. And if you want to have an explicit formula for the b n, it's not that bad either, and at some point in time we'll probably use it, but the only thing there is that chasing the negative sign is a bit of a pain, but it's nothing that's difficult in principle. Okay, except that the claim is that the integral can be taken over any circle around z0, with radius between r, and we're still depending on C capital R and C lowercase r. Well, let's take a look at that one more time. Remember that, or for the replacement of the circle C lowercase r and C capital R with any circle with radius between r and r, note that the integral of f of c divided by c minus c0 to the k over cr is the same over c lowercase r is the same as the integral over c uppercase r, and that's because if z0 is here and we go over c lowercase r backwards and over c uppercase r the right way around, we can do this standard link up technique, right? And we realize now that because the only singularity is at the center, that we're integrating an analytic function over a closed contour, so the total integral is 0, and that means if we now push this gap together, then this integral that goes in and this integral goes out, those will approximate the same number, and in the limit they will cancel each other, and that means that the integral over c capital R in the positive direction plus the integral over c lowercase r in the negative direction is equal to 0, which means that the integral over c lowercase r is equal to the integral over c uppercase r, and similarly the integral is the same over any circle around z0 with the radius between lowercase r and capital R. You just draw the same picture and you have a circle somewhere in between there. So that means these two integrals are equal to any of the integrals with over circles with radii in between, and that proves the claim. Okay, let's take a look at some examples how this works. First, let's find the Laurent expansion of f of z equals sine 1 over z around z equals 0. Well, and in many cases you really don't need to compute those ugly integrals, because you will probably use the fact that the functions you're working with already have expansions. For example, sine of z we know is the sum n equals 0 to infinity, negative 1 to the n divided by 2n plus 1 factorial z to the 2n plus 1. Now we just plug in 1 over z in here, and we get the sum n equals 0 to infinity, negative 1 to the n divided by 2n plus 1 factorial 1 over z to the 2n plus 1, and then we can turn that to the 1 over z to the 2n plus 1, we can turn that into z to the negative 2n plus 1, but that's already it. That is the Laurent expansion of sine 1 over z. And what the theorem does for us is not that it gives us the expansion. What the theorem does is it tells us that the expansion is actually useful, that the expansion actually converges, which means that the expansion can actually be used in computations. Let's find the Laurent expansion of f of z equals z plus 1 over z minus 1 on one hand for z between 0 and 1, and on the other hand for z between 1 and infinity, where I need an absolute value here. Let me stick that in real quick. Alright, there's the absolute value. And well, let's first look at z absolute value between 0 and 1. We have that f of z is z plus 1 over z minus 1. Really the problem is the division here. But we realize that that's z plus 1 times negative 1 over 1 minus z, and we know how to handle 1 minus z. So that's z plus 1 times negative the sum n equals 0 to infinity z to the n, which turns into negative sum n equals 0 to infinity z to the n plus 1, because we multiply by z, minus the sum n equals 0 to infinity z to the n. And if we now want to do an index shift, we said m equals n plus 1. Well, that means m starts at 1, goes to infinity. We get negative sum m equals 1 to infinity z to the m minus sum n equals 0 to infinity z to the n. And, well, that just means that the 0th term, which is 1, stands by itself. So we get a negative 1, because there's a negative out front. And everything else is doubled up, so we get negative 1 minus the sum n equals 1 to infinity 2z to the n. Okay, well, that's not too bad. Now let's take a look at the Laurent expansion for z absolute value between 1 and infinity. I think I should have just looked a bit more carefully at those slides. And we're back. Well, for 1 smaller z absolute value smaller infinity, we realize that 0 is smaller than 1 over z absolute value is smaller than 1. And for those, we would be able to use geometric series arguments again, and that's what we will do. So f of z is z plus 1 over z minus 1. Now we just expand with 1 over z, we end up with 1 plus 1 over z divided by 1 minus 1 over z, and now we do the same thing as before. This is 1 plus 1 over z times 1 over 1 minus 1 over z, which is 1 plus 1 over z times, and we're using the geometric series expansion, sum n equals 0 to infinity 1 over z to the n, which we can multiply out, sum n equals 0 to infinity 1 over z to the n plus sum n equals 0 to infinity 1 over z to the n plus 1. And exactly in the same fashion as before, we have that the 0th term here just gives us 1, and everything else is doubled up. So this is the sum n equals 1 to infinity 2 over z to the n plus 1. And again, we get one of those infinite Laurent expansions that actually has negative exponents all the way out to negative infinity. All right, that's the deal with Laurent expansions. So from here on out, if we have to deal with bi-infinite power series, as these things are also called, well, as long as the right hypotheses are satisfied so that the Laurent expansion converges, we will do so. And in fact, we are going to use these expansions to great advantage in solving, for example, rather ugly integrals on the real line that cannot be solved any other way. But that's the residue theorem. That's ahead. Right now, let's see, what are we going to do next? I think we're going to talk a little bit more about power series. Right. Okay, I'll see you for that. Bye.